here in nonlinear FEM. So we start with more or less more theoretical topic, which is a lecture, so maybe 1 hour, maybe a little bit more. And then we go over to a computer exercise. And this is the computer exercise from last week. Then Simon will take over to the exercise. Okay, but as always, the first 2 or 3 minutes are yours. You can ask any question regarding course, life, or everything you want, exam or something like this, or to the course. Okay, so take your time, 2 or 3 minutes, write your questions in the chat, and then we start. So I see there are no questions, very fine. So we start today with the lecture, and I have provided some lecture notes already, which we are fill up now together. And because we only have 1 hour of time, I hope that the most things are clear. And if not, we do it as always. You can ask questions in between. Okay, today, standard Kaioken method is the method that we always use in FEM. Today, we are talking about a so-called geometrically nonlinear finite element formulation related to the current configuration. To give some words before what we have done so far, we have related ourselves to the reference configuration. This is, I think, very standard. As you also have maybe seen in the script, you can work with P and F as variables, or for example, with the second pk and e, or with the second pk and c. All these things are equivalent and are, I would say, at the end, yes, maybe matter of taste. So here in the current configuration, the main idea is that we push all these variables in the current configuration and evaluate everything there. So now you would maybe ask why we should do this, because between all our operations are equal signs, so these formulations are equivalent to each other, but maybe we have some advantages in providing the stress function, or maybe some advantages in coding, or that means in coding, in calculation time. At the end, it's also a matter of taste, but I will give some remarks on this at the very special points in this lecture. So the starting point is again the balance of momentum, and this is given, of course, all of you know this, the divergence of P, the first pure Kirchhoff stress tensor, plus some body forces which will be neglected in the following. This is the equation where we start. And we start there also in the last lecture. The corresponding weak form is also given here. I have a delta G. And here we see P scalar multiplied with the scalar of the gradient of the test function, which is nothing else as the variation of F and some boundary terms and some volume terms. So this is the same as in the last 2 lectures. This is the basic. And now we take a closer look to this gradient symbol. And these maybe you have already recognized. Today, or until now, I have not used a nabla operator for certain reasons. I used the notation here where I make a large capital E. What's going on? Komische Sache. Here I used something. Here, for example, here, this diff and this grad are large capitals. So, and that means that these kind of operators are related to the reference configuration. If we now want to relate something to the current configuration, I want to introduce here something which you see here down below. In order to derive the spatial counterpart of the virtual world, we use the relation gradient of A is equal to something which I want to call now a small gradient of a vector A, and this I have to use, or I have to tensor multiply with an F. So now you may be wondering why we use this here in this case. Yeah, in order to shift something to the spatial counterparts, we not only have to shift tensors, so you know all from continuum mechanics that you can make a push forward for the second pk, for example, to tau or something like this. No, we also have moved our derivatives with respect, or we have moved our derivatives to the current configuration, and that is given here. I make it more slowly at this point. For example, here I have something as a vector A, and I make the derivative with the large capital X. That means this is nothing else than the large grad. To take a closer look, if I want to do this with respect to the current configuration, then I have to make a derivative with respect to the small x, Clear? This is the gradient of A. And then I have to make the derivative of small x, of small x with respect to large X. And this is, of course, known as F. I think all of you know this. And then we get here this formula. If you have a large gradient, you could replace them by a small gradient and a F. And of course, this works also vice versa. This is also a transformation or a rule, a mapping, or whatever you want to call it, where we use F as many, many other times also. Come on. So, okay. Yes, with this in hand, we obtain the weak form P scalar multiplied with the gradient is nothing else than a large gradient is replaced by the small gradient here. And then we could replace the F. So with a formula you have learned in tensor calculus, and if you are now in the second semester, you will go to this formula tomorrow. We could move, if we have a scalar product, and we have here a scalar product, and on the right side we have a tensor multiplication. We can move, for example, the right tensor, this is here the F, we can move them to the opposite of the scalar product, so we can move them to the P, also on the right side, but transposed. Okay, this is a formula from tensor calculus. And then we end up with P single multiplied or tensor multiplied with F transposed. This is nothing else than this nice tau at this place. And then we end up here with the weak form delta G. Now we have a small delta G in terms of somehow actual values, tau, and the small gradient of the displacements. Test function. The other terms are unchanged, and yes, now we have to make the same idea as in the other case. We make a linearization of this small delta G by means of the Newton's method. So this is the same what we have discussed last week or the week before. So linearized small delta G is of course the delta G plus a delta G. Delta G is already here, and we have now to take into account for the linearization delta G. Okay, how does it works? And here the first part, we restrict ourselves to conservative loads. Conservative load means, also given as dead loads, for example, means that the traction vector here, so this guy here, this is a constant. That means if I take a force, and the force is, of course, maybe I draw a small picture to this, that it maybe becomes clearer then. For example, you can have two situations. So first situation is here a beam, and I have a force, and then a deformation takes place. That means at the end I have something like this, and the force is also like that. This is conservative. If you have a non-conservative load, that means the same idea. Here I have 90 degrees angle, and I will use this. So that means this is a, let's say, a requirement or a constraint that this angle is the same always. Then I end up maybe with something like this, and then I have the force which looks like that. That means this is not conservative. The difference between that is a conservative load is never changes. So it never changed, a displacement occur, and the load is not changing its form. But you see in the second case, in a not conservative case, if here a displacement takes place, of course, because I have a deformation here, and then, for example, in this case, the load is rotating, so that means the load is displacement dependent. then I have to do the the linearization also for this term. In Abacus, this is a button. You can try this, and you see there the load is following the rotation or not. Okay. So we use here the conservative loads. That means I have only to use, or maybe I have only this term here. And this term is then split up in two terms. One of these is that one, and the other one is that one. So these are the two terms which are coming from the linearization. And here in the more formal words, I make the delta of tau times the gradient, and then I take tau and make the delta of the gradient. And with the latter one, we start here, and here we see, okay, delta of a gradient of variation of u. Normally we would say, the variation of u, there is no possibilities for deltas, but now we see that inside of the small gradient, we have another f. So the small gradient operator is, of course, related to displacements. Of course, the actual configuration is related to displacements, and of course, the spatial derivatives of that, of course, also. Okay, what we are doing first is we make here a retransformation to the large one. You can see this in the formula above. I have here, this is then the large gradient with respect to the reference configuration, and f up to the -1. Maybe this is not that good. So f to the -1. Okay, with this in hand, I could more or less define, of course, the large gradient test function. This is, of course, not related to displacement. That means here nothing is changing. But of course, I have here something like that. And now the question is, of course, what the hell is the increment, the linearization of f up to the -1? We have already this for of course, the increment or the variation of f we've discussed 2 weeks ago, but now we have to do this for the inverse of the deformation gradient. Okay, here we use a trick which is sometimes asked in exams, and this is the following idea. The linear increment of the inverse of the deformation gradient can be calculated accounting for f tensor multiplied with f up to the -1. And of course, I hope all of you know that this is equal to 1, it's the identity tensor. And if I make a linearization of this expression, the linearization of the identity tensor is obviously equals to 0. That means here I see delta f applied on f up to the -1 is equal to 0. Okay, with this in hand, we go into this formula and can define, if I make here the deltas, I can of course make the delta of the first one times the second one, plus, and here again, this first one applied with the delta of the second one, equal to 0. And I think this should be something like that. Okay, if I now apply f up to the -1 from the left, that means I have to apply f up to the -1 from the left side. I get the first part as f up to -1 applied on delta f, applied on f up to the -1. This is this, plus, yes, and of course here I have an identity. I have here f up -1 applied on f. This is equal to 1. That means here delta f up to the -1 is remaining. And from this I can derive delta f up to the -1 is equal to minus, and then this expression on the other side. I have to bring this with minus on the other side. Yes. And then with this in hand, of course, we could also make a further notation. I hope that you know this. Delta F is nothing else than the large gradient. Means here F up to the -1 applied on the large gradient of delta U, and this is with F up to the -1. And with this in hand, I can now go into the formula. That means here I have, this was our idea. So here I have to replace this guy, of course, with this guy, and this is then, of course, I missed. I'm not sure why. I'm sure I know why this is not working, but I hope that you know this. What I'm replacing now, and we obtain here something like that. So that means the gradient. So maybe I do it like that one here. So this guy here is equal to that guy here, and with this in hand, I end up then here with this line. The linearized So the linearized part of the small gradient is equal to the large gradient, delta U, applied on delta F inverse. Delta F inverse we have derived with all details. We have insert is into that, and then we see, oh, I have here the situation that we have here the large gradient with F up to the -1, and again a large gradient with F up to the -1, and at the end we all see we get here two small gradients, and like each term of delta something, here in this case delta small g, I have here delta U in terms of variation and a linearized version, and this is of course important for the stiffness matrix. Okay. The next term we discuss in 2 minutes is the term of tau, the linear increment of tau, as we see here above. Here, first term, here we have delta tau, and delta tau, and this is, I think all of you know this, is assumed to be tau is equal to F as F transposed, and of course I make the delta to the first, with the 2 second, then the delta in between, like we do this in the whole nonlinear lecture, and then of course the delta at the end. But what does it mean, and how we can transform them after all into the reference, into the spatial configuration, we will discuss in 5 minutes, and you have now time to ask questions to that what you are see here. I hope that it becomes clear. We have defined F inverse from the left. Yes, I have multi-tensor multiplied. Here, from the left. If I apply, this is from the left. Here I apply F up to the -1 from this side, and then I get the next line. I hope that's clear, Rajesh. If not, then ask me again in 5 minutes, but you can try on your own. This is nothing else from the left. I mean, if you have a tensor, you can apply from the right or from the left, and here I do it from the left. So, okay, take your time. I would say 5 minutes, and you could, perfect, Rajesh. And you can write your questions if there are any, of course, in the chat, and then we are continuing. So, one question. Professor, are we dealing with small strain here? I saw that you used epsilon for strain. I have used epsilon. No, Miklas, we are not dealing here with small strains. We are dealing here, geometrically nonlinearity are always large strains, and where I have used an epsilon. Also, until now, I do not have used an epsilon. Maybe, yeah.
Sorry, Professor. Actually, I thought that previously at the start of the page where you were coming from the solutions, I think I saw an epsilon there.
When? This page? Or
no, the starting, first page.
Here?
Yeah, here, Professor. Okay, sorry. It was my confusion. My bad, Professor.
Yeah, maybe it was my bad writing. This is a T.
No. Yeah, no. I confused. Sorry, Professor.
Okay, perfect. So, because at the end we use also something which looks like an epsilon, but anyhow, here in this case or in this course in nonlinear FEM, we are always treating large strains and have other strain measures. Okay. So now we are here at this point that we have to define what did we conclude with conductive loads? We did conclude that if you have this is a load. This load could rotating with the deformation or not. You see this in two things here. In the first kind, the load is straight again, so it's directing at, let's say, in case 1, and it is still here, it's 0 minus 1, and here it's also 0 minus 1. So that means the load is not interested in deformation. Here the load is 0 minus 1, and here the load is 0 minus 5, 0 minus 5. In this case, the load has changed its direction, so the load is dependent on displacements, and therefore it's non-conservative, and therefore we have to linearize it if we use non-conservative loads. So we use the first one, so we do not have to take into account this part here in the middle, and so we have only the yellow term for the linearization. I hope that is clear. So, perfect. So now we have here some deltas, and I will start with the first and with the, take another color. I take now into account the first and the last part. These two parts were discussed about these deltas and happening to them. So with this, so then this one is this one here and this one here. Okay, what we have now is, or what take into account is, if I have something like delta upon F inverse, or it's vice, or it's exactly the same, it's for the transposed. Here I have F minus transposed applied on delta F transposed, so the equivalent only in transposed form. I could rewrite this as, so the first step, now. In the first step, I replace this one here, so this one to this one. This is the first step. I know that delta F is the gradient of delta U, and then with this in hand, I use the formula, and then I finally arrive at the gradient, the small gradient of delta U. We have learned this already. Now I make a trick. And this trick is given here and here. So this trick, this I keep here. And this trick, you can see, the first thing I do is I insert a 1. And this one, needs of course color. This one here is that one here. Or in other words, this one here is this one here. That means by a trick, I include, maybe I make this a little bit larger so that you can see it here. In between here in between here, at this place, I introduce the one tensor, as in this case, f up to the -1 applied on f in the transposed variant, and then I get this line here. And with this trick, I could recognize, oh, very nicely, these two guys here now, I take another color. Maybe now I write this in red. These two colors here, no, red is the thing we are discussing. Let's make that one here. These two guys on the other side, these two guys are that one. Because what we know here, this is the starting line. That one here is that one at the end. By our yellow trick, it's a yellow trick. Oh no, this is not not that good. So again, I hope that you know what I mean. It is the yellow trick. I introduce a 1, and then I see very nice. Oh, there f applied on f up to the -1. This is a small gradient of u, and at the very, very end, I end up then here, and I see here something is missing. Here I end up then with these term here and here. So here I need to scalar product. So these are the trick. We use the first line in magenta or in pink, and then the yellow trick. And at the end, I have the two contributions for 1 and 3, which is equal to the gradient of the delta displacement with respect to the current configuration, scalar multiplied with the Cauchy stresses. That's it. Okay, so I hope, well, you can ask questions in 1 second. So this is, I would say, this is only a few mathematical manipulations. I think this is not a big deal here. So for the second one, we make maybe a bigger deal. And here we have, again, this is the second one. And here I use blue. This is the blue one. The blue one here is the linear increment of 2, which counting for the Solvent-Kirchhoff of material law appears as. And here we see, okay, there's one. Maybe I go back. Here you see this is now the guy what we are talking about. Okay, to the left and to the right I have two F's, quite fine. And in between I have something which is related to delta S. Okay, delta S. So what does it mean? Delta S is something like delta CE. So I hope that this here is double contraction. Maybe we make it a little bit more sure that it is a double contraction. 4th order tensor on 2nd order tensor. Obviously in C, as always, we have only material constants. It's a material tensor, and I have only apply the linearization to E. We have done this last or the week before. So now it's again a matter of taste. You could write delta E or 1/2 delta C. You see this in the script. My boss works, let's say in general, maybe more people working in 1/2 delta C. I, for myself, if you are new to the stuff in nonlinear FEM, I would always prefer delta E, because it's for the brain, it's maybe a little bit more, it's better to recognize something which you have already in a similar sense from a FEM foundation. But again, at the end, it's an equal sign in between. It's a matter of taste. Something which is important is here, I have to replace these deltas with 1/2, and then this is clear. I have delta F transpose F plus F transpose delta F. And here we play the same as before. I have this remarked already, so this is not the yellow trick, this is something different, nothing to do with yellow. I have done, insert here this, delta F is a small gradient of U with F, and the same holds for the transposed. So I have replaced here these terms, that term and that term, from these and these equations. So this is done until now on this page here. Okay. So now I have already here small gradients in here, and I have to reformulate this a little bit. First of all, I have to include here, so I leave the outer f's. That means here I start again with an f. This is the outer f. Here nothing changes. Then I have here, of course, the large bracket. Again, the c takes place and a double construction with something, and now I change something inside of these formula. As you see here, all the terms here, that means I have here, I make this now in blue in order to take another color. So here, for example, I have a transposed, and here I have a transposed, and here I have an f, and here I have also an f, and that means I could use these f's outside of these again another bracket. That means here on the left I have an f transposed times, and then here 1/2 of something which is left. In this case, this is the gradient transposed of delta u, plus the gradient of delta u, and on the other side the other f remains, and outside another f transpose is remaining. So that means I have introduced here, no, not introduced, I have made another sortation here in blue. I have this on that side and that on that side, and I end up here with these expression now. Now I introduce something which is really looking like small strain, therefore I wonder myself the question before. This one here, for example, is now defined but not as an epsilon. This is now defined as something which I want to show you as delta small e. This is because this tensor looks identically to a small strain epsilon. The only thing which is now changing is the gradients. In a small strain world, I have, of course, a large gradient, which is not related to displacements. But now here, I have a small gradient, which is obviously related to the displacements, and therefore also at the end non-linear. But only to introduce here something, I want to use this here for this as a, let's say, new kinematic tensor. And with this in hand, I finally end up here with something which looks like that. I have here an f. Then I stem up here with another C. I got here something which I would show you as F transposed on this delta. Looks like a euro sign, or similar, and an F. And this is then accomplished with the outer F transposed. Okay, so, and now you see something which will now reformulate it to, and here I have this complete expression. Maybe I write it again. Here I have, this is exactly the same as before. I write it only again in order to make it precise. So this is the whole expression. I want to draw your attention to the F's. It means I have here a C. I have here a small, let's say, kinematic rule, delta small e, and I have 4 F's. And this I want now to rearrange, and we do this in 5 minutes, to something which is a small c applied to delta e. And how this works, we do in 1 second, but until here, again, you could take your time and ask question to this funny picture where we have many colors. So we make the linearization. So we finish the linearization. We have the only thing what we have to determine for the implementation is this small c. What's going on with the small c, with the small constitutive c. And what we see here else is nothing else than no. Hasini, this is not the small e. This is something different. Maybe I give this in 1 second. What we have done here is linearization of term 1 and 3 with this yellow trick, and then with these yes, F transpose and Fs, and here we move them to the right hand side. Very important, I do write it here. This is not the same as that. It's not the same. This is linear. And we make nonlinear theory. It looks similar, but it's of course not the same. Okay, so take your time. Asini, I have no idea. No, I'm not sure about it, if they have official names. I think about this, and you could find now maybe 5 minutes for questions, and I take 5 minutes in order to think about official names for these two things. So, okay, maybe there are some questions to the linearization. Or maybe Simon knows the official names of these two expressions. So I see there's no one writing, so I think there are no questions or no further questions to that. And now we are going to examine what is this small c. So this is of course a fourth order tensor, and somehow so we have these two lines here, and somehow all the four f's disappear in a magic way, and enters then in this small c, and this is then together with this new strain measure. Okay, so in order to do so, we need some tensor calculus, and this is given here by that way, or in this sense. You have to remember, so we are interested here, I think that was the blue one here, very important. Delta of the Kirchhoff stresses of the second term is of course somehow related to the actual configuration, and now I introduce here a special notation which is preferred by my boss, and here very useful. And we have here a small letter is a small letter indices. So we have here index notation, of course. What we see here is index notation, very important. We have here a small letter is an actual configuration index, and a uppercase letter, so the large A, is a reference configuration index. That means F, for example, is a two-field tensor. Here I have here AA. That means it's not the same. It's like Fij. There are two different indices. Yes, both of them have an A as name, but of course this is different. Okay, I have FAA, then delta SAB, curse second pk is in the reference configuration, large AB, and then I close with S transposed, and here that means I have a small b and then a large b. You know this from last time. Here SF transposed, the second index, is the index which is connected to each other. Okay, so what we know is that I have SAB, the delta SAB is of course something which is normally related to the constitutive tensor. C is fourth order, A, B, C, D, and something which is remaining of that. And that what is remaining here must have the index of CD. If it's not the case, then it's not working. Okay. So take a closer look at that, and this is now, we have to find out that this expression here, F transposed applied on this new strain measure, applied on F, at the end have the index of CD. With this in hand, the only idea which works here, the first is a transpose, that means the first index here is related to the summing up index, so this is like F transposed F. We have also discussed this 2 weeks ago. And then, of course, we know this new strain is completely related to the current configuration, so I have here a small CD. And then, of course, the second F contains also a D small and then a D large, and this is inside of these bracket, the upper line in direct notation, in the lower line in index notation. And with this in hand, we can move, so don't forget, I have here on the left and the right, I have additional two Fs. So you see, inside of delta second pk, I have two Fs, and outside I have another two Fs. So if I put them all together, I end up here with this line. Again, I'm talking about the second part of the Kirchhoff stress linearization, and I end up here with a holy mess. So I have here, of course, my new strain measure. This is the small new strain measure, and then I have a C, fourth order C, and four Fs, four deformation gradients. And maybe I want to draw your attention again to continuum mechanics. If you want to make a push, for example, you want to make a push of the second pk, this is a second order tensor, then you need two Fs, and you end up with F, S, F transposed, and the new name is tau. So this is the push forward of S to tau. Of course, this works vice versa. And the most important rule here is, if you want to push a vector, for example, then you need only one F from the left to the right. If you want to push a second order tensor, then you need two Fs. And straightforward, if you want to push a fourth order tensor, then you need four Fs in order to push each basis, capital A, capital B, capital C, and capital D, to the actual configuration that looks like that. And then you end up here With this rule, in index notation, you can make a sortation like you want. And here you can see the small c, a, b, c, d is nothing else than the c, or is nothing else than also fourth order tensor, but is now included are 4 f's. And this could, of course, in the finite element code, this could be done every time. If you have an f, so if you have a symmetric, if you have a displacement gradient, then you have an f, and then you can make this this mathematical rule or mathematical formulation, and then you end up here in this formulation for this expression. Again, here maybe this is a maybe it's new at the end, it's tensor calculus somehow and a little bit continuum mechanics, but maybe take your time again, 2 minutes if you have questions to this reformulation of the constitutive tensor, and then I'm back. Okay, again, no further questions. Very nice. Okay, so now we come to the end of the lecture. We have now all the parts. So this is the part, so the second part of the linearization. We have already the first and the third part for delta tau, and of course at the very, very beginning we have learned how to make a linearization of the spatial gradient, and now of course we put everything together. That means the increment of the Kirchhoff stresses appears here. So maybe I give you the impression where we started here. So here we started delta tau. We have show or see all the linearizations, 1, 2, 3. We have done them and pushed them in the actual configuration, and then we end up here with this line. And yes, of course, there are three things, three components. And furthermore, we see here then all these terms, and I have already provided something in dark green and in light green. Again, so I repeat this very shortly. Delta delta G, so in each term I need at least two deltas, so a test function or a variation, and of course an increment, a large delta. And I have here the first expression, maybe, so this was here the expression what we have derived here. This is delta tau times the variation of that guy, and the other one here, this comes from the delta of the variation of the gradient of the variation of the displacements. Okay, so these are all the terms we have derived, and now again we use the formula which you are, as before, which you are using tomorrow in tensor calculus, most important transformation in the world. Here we see that these terms, one have a plus and the other one have a minus, are equivalent because, again, here, if you go on this side, for example, you have here a scalar multiplication. On the left side, we have a tau. On the right side, we have a tensor multiplication between two tensors. And now you are allowed to put one of these tensors from the right side of the scalar product to the left side of the scalar product, but transposed. That means here we take the gradient, which is on the right side of the scalar product and on the right side of this tensor multiplication, so, and return them on the other side, and then we end on. And then we end up here with this formula. On the right side of the scalar product, the gradient of the variation of u is standalone, and then we have on the other side a tensor product, but here again on the right side the gradient of the increment of u, but now transposed. And here, if you use that rule, then you see that these two terms in light green are the same, and we end up then with, so one is plus, one is minus, and then the very, very final form is that one here. This is then delta g. So this is a transformation. You can use also the script where you find the same result, maybe in a different declaration, but again, you can use different ways here with tensor calculus to end up with this formulation, and this could then be, or is then the basis for any further coding. At the very, very end, two terms. Here again, like in the reference configuration formulation, we have a material stiffness and a geometrical stiffness part, so part of the stiffness matrix. Here we introduced the variation of our new strain measure, which is of course given here by this formula. It's of course the same, only with other deltas. And then you see this looks, so the first part and maybe also the second part looks somehow similar to the reference configuration, but at the end it is related somehow to measurements and gradients for the current configuration. And even we have a new constitutive C fourth order tensor, which includes now 4 F's inside. Okay, again, I think so here at the end, I hope that this is not very complicated. We have put everything together and make here plus and minus, but again, maybe 1 or 2 minutes in order to you to get through this, which I upload at the end, and maybe have some questions. Okay, I'm back in 2 minutes. So we have one question here from Miklesh. I'm not sure if this strain measure have a physical meaning, to be honest. And of course, you could use other strain configuration, other strains from the actual configuration. But something which is very important here, of course, there are very, very, very different, let's say, geometrically non-linear elasticity formulations. This one we have discussed here, and what you are coding in 1 second, is, I would say, the simplest one. Here we already have used a so-called Sauvenor material law, so in both of them. And this Sauvenor material law is restricted to the, of course, to the tensor E, to green Lagrange, or let's say to the right Cauchy green. And we have done this in order to use this fourth order tensor C. If you go over to other material laws, for example, Neo-Hook, Mooney, Rivlin, Baruda-Boys, Ogden, there are many, many of them, then you will have automatically different strain measures, which are completely different to that what we have discussed here, for example, C up to the -1 or the Kani-Reiner, but there are different others. But for this special, let's say, most simplest formulation in the world, so Sauvenor-Kirchhoff, we end up with these, so with the well-known green Lagrange, and with this, let's say, new one, where we do not know the name, which looks like a small strain. It looks like similar or optically to a small strain measure, but I'm not sure if this have a name. And the need is maybe also with respect to something we know. I think it have computational issues in order to use these kind of formulations. So I have never used exactly this one. So I have used in my life actual configuration laws, but not in this sense. But for example, I know, and therefore it's worth talking about that. For example, if you are using Abacus and you want to implement user material, then Abacus wants to have something similar to that. So Abacus wants the Cauchy stresses and the so-called Jaumann rate. This is something which is similar to that what we have to discuss today. And there you also could ask yourself why they want to have exactly these measures. So I'm not sure. I think it's maybe the computation time. And yeah. But anyhow, okay, Miklesh, I hope this is more or less good argumentation for the question. Okay, so now we are finished with the reference configuration theory. I will upload them. You see at the end, it's equivalent to that what you are doing now with Simon in the exercise. Yes, matter of taste. I think computation. And at the end, for example, if you are introducing B matrices, here for that guy, they look exactly like a small strain B matrix, only with derivative respect to the current configuration. Okay, so we are finished. Again, I want to thank you for your attention. Merry Christmas, Happy New Year, and we see us, I think, at 11th of January with a special lecture on mixed fab. Okay, so Simon, du darfst.
Ja. Okay, hello everybody. Und hallo Alex. Telefonieren wir da einmal gleich kurz, nachher?
Ja, wann magst du?
Ja, sonst rufe ich einfach an, wenn ich hier fertig bin.
Ja, nee, also glaubst du brauchst du zu lange oder eher nicht?
Ich denke nicht, sagen wir es mal so. Mal gucken.
Okay. Nee, ruf einfach an.
Gut, bis später.
Jo, bis später. Ciao.
Okay. First of all, I will take presenter rights. Okay, as I told you last time, today we will basically continue with the exercise of last time. So we want to implement or finish the implementing of the 2D element. I think some of you, or hopefully most of you, already did that. So first of all, I want to give you a short review on the results which we want to have in the end. So I gave you a few